Introduction to FortiGate SD-WAN multi-hub design. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will dive deep into FortiGate SD-WAN multiple hub design. This is a critical architecture pattern for enterprises that need resilient, scalable, and geographically distributed wide-area networks. We will cover why multi-hub designs exist, how they are built, and walk through the actual FortiGate command line interface configuration required to make them work. Multi-hub SD-WAN is not just a redundancy play. It is a fundamental architectural decision that affects routing, performance, failover behavior, and operational complexity. By the end of this series, you should understand how to design a multi-hub topology, configure both the hubs and spokes, define SD-WAN zones, apply performance SLAs, and steer traffic intelligently across multiple hubs based on application requirements. We will use the FortiOS CLI throughout because that is where the real work happens. While the GUI gives you a starting point, production multi-hub designs are almost always rolled out through scripts, templates, or the FortiManager, all of which generate the same CLI commands we will examine directly. Multi-hub topology design. Let me walk you through the multi-hub SD-WAN topology diagram step by step. This diagram illustrates the core architecture we will be building throughout this presentation series. At the core of the design, we have two hubs labeled Hub 1 and Hub 2. These are FortiGate firewalls typically deployed in separate data centers or separate public cloud regions. Hub 1 might live in a primary data center such as US East 1 in AWS, while Hub 2 lives in a secondary data center such as US West 2. The separation is intentional, so that a failure of one entire region does not take both hubs down at the same time. Each hub connects to two underlay transports. The MPLS cloud represents a private carrier network, providing predictable latency and guaranteed bandwidth. The Internet cloud represents the public internet, providing broadband connectivity that is cheap and widely available but without any service guarantees. Both hubs connect to both transports, which means each hub has at least two public-facing IP addresses, one reachable over MPLS and one reachable over the Internet. On the branch side, we have Spoke 1 and Spoke 2 representing typical branch office FortiGate devices. Each spoke also has connections to both the MPLS transport and the Internet transport. This dual transport design is fundamental to SD-WAN because it gives the box two independent paths to choose from, and the SD-WAN logic decides which path to use for any given application. Now look at the overlay tunnels. Spoke 1 builds an IPsec tunnel to Hub 1 over MPLS and a separate IPsec tunnel to Hub 1 over the Internet. It also builds an IPsec tunnel to Hub 2 over MPLS and an IPsec tunnel to Hub 2 over the Internet. That is 4 overlay tunnels from a single spoke, which is the defining characteristic of dual hub dual transport SD-WAN. Spoke 2 follows the identical pattern, building its own 4 overlays to the same hubs. The result is a fully meshed overlay fabric where every spoke has multiple paths to reach services behind either hub. If Hub 1 over MPLS degrades, traffic can shift to Hub 1 over Internet, or to Hub 2 over MPLS, or to Hub 2 over Internet. This is the source of the resilience that justifies the design complexity. Hub ADVPN configuration. Now let us look at a critical feature for multi-hub SD-WAN, which is ADVPN, short for Auto Discovery vPages N. Without ADVPN, every packet between two spokes has to transit the hub, which creates a traffic trombone. With ADVPN, the hub tells two spokes about each other when they first need to communicate, and they build a direct shortcut tunnel, cutting the hub out of the data plane for that conversation. Let me walk you through this ADVPN sequence diagram. The sequence begins when Spoke 1 needs to send traffic to a destination that belongs to Spoke 2. Spoke 1 sends the initial packet through its existing tunnel to the hub because that is the only path it currently knows. The hub receives the packet and performs a route lookup. It sees that the destination belongs to Spoke 2, which is also connected as a dial-up peer. Rather than simply forwarding the packet, which would work but is inefficient, the hub recognizes this as an opportunity for a shortcut. The hub sends a shortcut offer message back to Spoke 1, containing the information Spoke 1 needs to reach Spoke 2 directly. This includes Spoke 2's public IP address, its Phase 1 proposal details, and the authentication information. At the same time, the hub forwards the original packet onto Spoke 2 so that no traffic is lost during the setup. The hub also sends a shortcut offer to Spoke 2, notifying it that Spoke 1 wants to establish a direct connection and providing Spoke 1's reachability information. This parallel notification is important because IPsec negotiation needs both sides to be prepared. Spoke 1 then initiates an IKE negotiation directly to Spoke 2 using the information it received from the hub. Spoke 2 is ready for this negotiation because it was pre-notified. The two spokes complete IKE Phase 1 and Phase 2 negotiation over the underlay without the hub being involved in this exchange. Once the shortcut tunnel is up, Spoke 1 and Spoke 2 exchange routing information, typically through BGP running over the new tunnel. From this point forward, all subsequent packets between Spoke 1 and Spoke 2 flow directly through the shortcut tunnel, bypassing the hub entirely. The hub remains involved only for control plane operations and as a fallback if the shortcut tunnel ever fails. The configuration to enable this on the hub requires 3 parameters on the Phase 1 interface. The Set Auto Discovery Sender Enable command tells the hub to send shortcut offers when it detects spoke-to-spoke traffic opportunities. The Set Auto Discovery Receiver Enable command allows the hub to accept shortcut information from other hubs in more complex designs. And the Set Add Route Disable command prevents the hub from automatically adding routes learned via mode config, letting us control routing explicitly through BGP instead. SD-WAN zones and interface membership. Now that we have 4 overlay tunnels on each spoke, we need to organize them into SD-WAN zones. Zones are FortiGate's way of grouping interfaces that share a common role or purpose, so that SD-WAN rules can reference the zone rather than listing every member interface individually. Let me walk you through this SD-WAN zone membership diagram. At the core of the SD-WAN configuration is the SD-WAN virtual interface, which is a container that aggregates multiple physical and logical interfaces under a single policy and routing domain. Inside the SD-WAN container we define 3 zones. The first zone is named overlay_MPLS, which groups together all tunnels that ride on the MPLS transport. The overlay_MPLS zone contains H1_MPLS, which is the tunnel to hub 1 over MPLS, and H2_MPLS, which is the tunnel to hub 2 over MPLS. Both of these share the characteristic of using the private MPLS network as their underlay. The second zone is named overlay_INET, which groups the tunnels riding on the public internet. The overlay_INET zone contains H1_INET, the tunnel to hub 1 over the internet, and H2_INET, the tunnel to hub 2 over the internet. These share the characteristic of using the public internet as their underlay. The third zone is named underlay, which contains the raw physical WAN interfaces port 1 and port 2. We include the underlay zone in SD-WAN because some traffic, particularly direct internet breakout for software as a service applications, should not be encrypted into an overlay but should instead go directly out the local internet interface. The underlay zone gives us a policy hook for that local breakout behavior. The configuration begins with config system SD-WAN to enter SD-WAN mode, followed by set status enable to turn on the SD-WAN feature. The config zone subsection defines each zone by name. Then under config members we assign each interface a sequence number and associate it with the correct zone using the zone parameter. Sequence numbers are just internal identifiers and do not affect path selection priority. This zone-based model is powerful because when we later write SD-WAN rules, we can say things like send this traffic to overlay_MPLS zone with a particular load balancing strategy, and FortiGate will automatically distribute the traffic across H1_MPLS and H2_MPLS according to the chosen algorithm. We do not have to list the individual tunnels, and we do not have to rewrite the rule if we add a third hub later. SD-WAN rules for hub selection. SD-WAN rules, also called service rules, are where all the previous configuration pays off. These rules match traffic based on source, destination, application, or other criteria, and they specify how that traffic should be steered across the available paths. The config system SD-WAN and config service commands enter the service rule configuration area. Each edit block creates a numbered rule. Rules are evaluated top to bottom, so rule 1 is evaluated first, and the first matching rule wins, so ordering matters significantly. The first rule, edit 1 with name voice to HUB1, is for voice traffic. The set destination 10.100.0.0/16 matches traffic destined for the data center subnet behind HUB1. The set Internet Service Application Control Line is omitted in this example but could be added to match specific applications like Ring Central or Microsoft Teams. The set mode SLA parameter selects SLA-based path selection, which means FortiGate picks any member that is currently meeting the SLA thresholds, and if multiple members meet SLA, it uses them in order of preference. The set health check HUB_health associates this rule with the health check we defined earlier. The set SLA HUB_health1 references the specific SLA identifier we want to enforce, and set priority members 1-3 lists the members to use in order of preference, where member 1 is H1_MPLS as primary and member 3 is H2_MPLS as backup. Voice traffic prefers MPLS because of the predictable latency and jitter. The second rule, edit 2 with name BULK_TO_HUB1, handles bulk data traffic like file transfers or backups to the same data center. The set destination 10.100.0.0/16 matches the same destination as the voice rule. But set mode manual this time uses manual path selection, which just picks the first available member without considering SLA. The set priority members 2-4-1-3 orders the members with Internet first. Open H1_INET and H2_INET and MPLS as fallback. This is intentional because bulk traffic is not latency sensitive, and we want to preserve the expensive MPLS bandwidth for voice and other sensitive applications. The third rule, edit 3 with name critical_to_hub2, is for traffic to applications hosted behind hub2, such as the secondary data center. The set destination 10.200.0.0/16 matches the hub2 data center subnet. The set mode SLA with the hub_health check enforces quality requirements. The set priority members 3-1 prefers H2_MPLS first because hub2 is the primary location for these apps, and then falls back to H1_MPLS to reach them via cross-hub routing if hub2 is unreachable. This illustrates an important multi-hub pattern, which is that even though each hub has a primary set of applications, the spokes can still reach hub2 applications through hub1 if needed. The set mode parameter has several other options worth knowing. The load balance mode distributes traffic across members using session-level balancing, which is useful when you want to aggregate bandwidth. The priority mode always uses the first available member in the list, only falling back if that member is down. Understanding these modes lets you match the path selection behavior to the traffic type. Verification and operational commands. Configuration is only half the battle. The other half is verifying that the configuration is working and troubleshooting when it is not. FortiGate has a rich set of diagnostic commands specifically for SD-WAN and IPsec that every engineer operating a multi-hub design needs to know. The Diagnose Sys SD-WAN member command shows the operational state of each SD-WAN member, including whether it is up or down and which zone it belongs to. This is usually the first command to run when investigating any SD-WAN issue because it tells you at a glance which tunnels are currently considered usable by the SD-WAN engine. The Diagnose Sys SD-WAN Health Check command shows the current state of every health check, including the measured latency, jitter, and packet loss for each member, as well as whether the member is meeting or violating the configured SLA thresholds. If a tunnel is up but continuously failing SLA, this command tells you which metric is out of range, which guides your next steps. The Diagnose SYS SD-WAN service command displays the service rules and shows which members are currently selected for each rule. This helps you understand whether the path selection logic is producing the result you expect. If voice traffic is going out internet instead of MPLS, this command will reveal why, usually by showing that the MPLS member is out of SLA. The Get Router Info Routing Table All command displays the routing table after all SD-WAN and BGP processing. Multi-hub designs rely on dynamic routing, typically BGP, running across the overlay tunnels, and this command confirms that routes are being learned from both hubs correctly. If only Hub 1 routes appear and Hub 2 routes are missing, that usually indicates a BGP neighbor issue on Hub 2 or that Hub 2 tunnels are down. The Diagnose VPN IKEE Gateway List command lists all active IKEE gateways with their state, remote peer, and encryption details. The Diagnose VPN Tunnel List command shows all active IPsec tunnels including a DVPN shortcut tunnels that have been dynamically created. Seeing a healthy mix of configured hub tunnels plus a few dynamic shortcut tunnels confirms that a DVPN is working as intended. Finally, the Diagnose Sniffer Packet Any Host 10.10.10.1.4 command captures live traffic matching any host on the specified overlay network, giving you packet-level visibility when logs and counters are not enough. This is invaluable for debugging asymmetric routing, MTU problems, or policy mismatches that only show up when you can see the actual packets. In the next part of this series we will dig deeper into BGP over IPsec configuration, BGP community tagging for path preference, route reflector designs for large-scale deployments, and how to integrate multi-hub SD-WAN with existing enterprise routing. We will also walk through failure scenarios and show exactly how traffic moves when a hub or a transport fails. BGP over IPsec for multi-hub SD-WAN. Welcome back to part 2 of the FortiGate SD-WAN multi-hub series. If you have not watched part 1, please go back and review it, because this part builds directly on the IPsec, zone, and SLA configuration we established there. Please consider subscribing to the channel and hitting the bell icon for notifications on the remaining parts. In part 1 we built the underlay tunnels and the SD-WAN policy engine. But we did not yet address a fundamental question, which is how do spokes actually learn where to send traffic? BGP over IPsec for multi-hub SD-WAN. Welcome back to part 2 of the FortiGate SD-WAN multi-hub series. If you have not watched part 1, please go back and review it, because this part builds directly on the IPsec, zone, and SLA configuration we established there. Please consider subscribing to the channel and hitting the bell icon for notifications on the remaining parts. In part 1 we built the underlay tunnels and the SD-WAN policy engine. But we did not yet address a fundamental question, which is how do spokes actually learn where to send traffic? Static routes would work in a tiny lab but do not scale to real enterprise multi-hub deployments. For that we need dynamic routing, and the standard choice in FortiGate SD-WAN is BGP. Let me walk you through this BGP neighborship diagram step by step. The diagram shows the control plane relationships that sit on top of the data plane overlays we built in part 1. Hub 1 and Hub 2 are the two FortiGate hubs, each running a BGP process. Both hubs are configured with a private autonomous system number, in this case 65,000, which is the same AS number on both hubs. This is a deliberate design choice. When all devices share the same AS number, we are running internal BGP, or IBGP, which behaves differently from external BGP in terms of route advertisement rules and attribute handling. Spoke 1 and Spoke 2 are the branch FortiGates, and they also run BGP with AS65000. Each spoke establishes BGP neighbor relationships with the hub over the overlay IPsec tunnels. Spoke 1 peers with hub 1 over the H1_MPLS tunnel overlay IP and separately peers with hub 1 over the H1_INET tunnel overlay IP. It also peers with hub 2 over both H2_MPLS and H2_INET. That is 4 BGP sessions from a single spoke, 1 per overlay tunnel. The IBGP session between hub 1 and hub 2 is also visible. This hub-to-hub BGP session is what enables cross-hub routing, meaning hub 1 can learn about prefixes connected to hub 2 and vice versa. Without this session, spokes connected only to hub 1 would have no visibility into hub 2 services, and you would not have a unified enterprise routing domain. The arrows labeled route advertisements indicate the direction of BGP update messages carrying prefix information. Spokes advertise their local LAN subnets to the hubs. Hubs advertise the consolidated prefix list, including data center prefixes and prefixes learned from the other hub, back down to all spokes. This creates a full mesh routing view even though the tunnel topology is hub and spoke. Spoke BGP configuration. The spoke BGP configuration is more explicit than the hub configuration because the spoke knows exactly which peers it needs, whereas the hub accepts a dynamic population. The spoke defines 4 static neighbors, 1 per overlay tunnel. The config router BGP context and set AS65000 mirror the hub configuration because we are running IBGP across the entire fabric. The set router ID 10.10.10.2 sets the spoke's router ID to its MPLS overlay IP. Every device in the BGP domain needs a unique router ID, and using the overlay IP makes allocation straightforward. The config neighbor context defines static BGP peers. The first edit 10.10.10.1 creates a neighbor statement for hub 1's MPLS overlay IP. The set remote AS65000 establishes this as an IBGP session. The set update source H1_MPLS ensures BGP traffic to this neighbor flows specifically over the H1_MPLS tunnel, preventing accidental routing of control traffic through the wrong path. The set soft reconfiguration enable lets us apply incoming policy changes without tearing down the BGP session, which is useful for maintenance windows. The set connect timer 10 and set advertisement interval 1 tune the BGP timers. The default BGP connect timer is 120 seconds, which is too slow for SD-WAN where we want fast convergence. Setting it to 10 seconds means the spoke will retry a failed session every 10 seconds. The advertisement interval of 1 second reduces the minimum time between BGP update messages, which helps spokes react quickly to topology changes. The subsequent neighbor blocks repeat this pattern for the other 3 tunnels. Neighbor 10.10.10.3 is hub 1 over the internet overlay with update source H1_INET. Neighbor 10.20.20.1 is hub 2 over the MPLS overlay with update source H2_MPLS. Neighbor 10.20.20.3 is hub 2 over the internet overlay with update source H2_INET. After these 4 blocks are applied, the spoke will establish 4 independent BGP sessions, receiving route advertisements over all 4. The config network command defines the prefixes this spoke will advertise into BGP. The edit 1 creates network statement 1, and set prefix 172.16.1.0255.255.255.0 advertises the spoke's local LAN subnet. This is how the hubs and other spokes learn that 172.16.1.0/24 is reachable through this spoke. Each spoke would have its own unique network statement matching its unique local subnet. The set eBGP enforce multi-hop enable is not needed here because we are using iBGP. But in scenarios where you use eBGP, this command would be required because the BGP peer is more than one hop away through the overlay tunnel. BGP community tagging. BGP communities are a tagging mechanism that lets you attach metadata to ROT advertisements. In multi-hub SD-WAN, communities are how we tell receiving routers what transport a ROT came in on, which hub originated it, and how it should be treated. This metadata then drives path preference decisions through ROT maps and filters. The configure router ROT map context creates named ROT maps that match on conditions and set BGP attributes. The first edit set_COMM_MPLS defines a ROT map that we will apply to inbound BGP advertisements read over MPLS overlays. Inside the ROT map we define sequence numbers, similar to access list entries, where each sequence defines a match and set action. The config rule in edit 1 creates rule 1. The set action permit says that matching ROTs are permitted to pass, which is typical for a tagging ROT map because we are not filtering but annotating. The set community 65000:100 applies BGP community 65000:100 to every matching ROT. The community format is two 16-bit numbers separated by a colon, where convention says the first number is the local AS and the second is a meaningful tag value. Here 100 means this ROT was learned over MPLS transport. The second ROT map SET_COMM_INET follows the same pattern but tags with community 65000:200, where 200 represents internet transport. When we apply these ROT maps on the hub inbound from the appropriate overlays, every prefix the hub learns gets tagged with its source transport. We can also tag by hub. The ROT map SET_COMM_HUB1 applied on hub 1 adds community 65000:1000 to indicate hub 1 as the learning hub. The matching ROT map SET_COMM_HUB2 on hub 2 adds community 65000:2000. After this double tagging, every prefix in the BGP fabric carries two communities, one for hub and one for transport, giving us rich path preference data. The config router community list command defines named community lists that other ROT maps can match on. The edit com_MPLS_ only creates a list that matches only community 65000:100, which we use later to give MPLS learned ROTs higher preference. The edit com_INET_ only matches only community 65000:200. These community lists act like object groups for BGP policy and make the subsequent ROT maps cleaner and more maintainable. The application of these ROT maps happens on the neighbor statement using the set ROT map in command. Applying set_COMM_MPLS inbound on all MPLS overlay BGP neighbors ensures every prefix learned from those neighbors receives the MPLS community tag before it enters the BGP table. This preserves the provenance of the ROT through subsequent hops. Cross-hub routing flow. Let me walk you through this cross-hub routing sequence diagram. It shows how a packet from Spoke 1 ultimately reaches a destination that lives behind Hub 2's data center, traversing the cross-hub BGP routing we have been configuring. The scenario starts with Spoke 1 needing to reach IP 10.200.1.5, which is a server in Hub 2's data center. Spoke 1 has BGP sessions to both Hub 1 and Hub 2, so it has learned the prefix 10.200.0.0/16 from both sources. Because of our community tagging and local preference manipulation, Spoke 1 has selected the path through Hub 2 with a higher local preference, even though it has a path through Hub 1 available. Spoke 1 sends the initial packet destined to 10.200.1.5 into its H2_MPLS tunnel, which is the tunnel to Hub 2 over the MPLS transport. The packet is encapsulated in IPsec and traverses the MPLS underlay. Hub 2 receives the packet, decapsulates it, and performs a route lookup. The destination 10.200.1.5 is directly connected to Hub 2's internal LAN interface, so Hub 2 forwards the packet out that interface toward the destination server. The server receives the packet, processes it, and generates a response. The response packet destined back to Spoke 1's LAN subnet arrives at Hub 2. Hub 2 looks up the destination 172.16.1.0/24 and finds that it learned this prefix via BGP from Spoke 1 over overlay tunnels. Hub 2 forwards the response packet into the overlay tunnel back towards Spoke 1. The SD-WAN logic on Hub 2 picks the specific tunnel based on the service rules and health checks, but in this example we assume it picks H2_MPLS for the return path as well, creating symmetric routing. Spoke 1 receives the return packet, decapsulates the IPsec header, and delivers it to the originating client on its LAN. The session completes with a predictable, BGP-driven path selection that prefers Hub 2 for Hub 2 home destinations. Now consider the scenario where Spoke 1's H2_MPLS and H2_INET tunnels both go down, perhaps due to a Hub 2 outage. Spoke 1's BGP sessions to Hub 2 drop, and the 10.200.0.0/16 prefix learned from Hub 2 is withdrawn. BGP reconverges and selects the alternative path learned from Hub 1. Because Hub 1 and Hub 2 peer with each other and Hub 1 has the same prefix in its BGP table, traffic now flows Spoke 1 to Hub 1 over H1_MPLS, then from Hub 1 to Hub 2 over the hub-to-hub link, and finally from Hub 2 to the destination. The cross-hub path adds latency but preserves connectivity, which is the entire point of a multi-hub design. Failure scenario: full hub down. Let me walk you through this hub failure sequence diagram. A full hub outage is less common than a transport failure but far more consequential, because it removes an entire routing target from the fabric. The multi-hub design exists primarily to handle this scenario gracefully. Steady-state operation has Spoke 1 with all 4 overlay tunnels up. Traffic to Hub 1's data center prefix 10.100.0.0/16 flows through H1_MPLS as the primary path. Traffic to Hub 2's data center prefix 10.200.0.0/16 flows through H2_MPLS because of our local preference steering. Hub 2 then suffers a complete failure. This could be a power outage in the data center, a catastrophic hardware failure, a software crash, or a regional cloud provider outage. All Hub 2 services go offline simultaneously. On Spoke 1, both the H2_MPLS and H2_INET tunnels lose their remote peer. i.e. dead peer detection fires on both tunnels, typically within 20 to 30 seconds depending on DPD timer configuration. The tunnels are declared down. SD-WAN health checks targeting Hub 2's overlay IP 10.20.20.1 begin failing immediately, and within 2.5 seconds both H2_MPLS and H2_INET are marked out of SLA. The SD-WAN service rule for 10.200.0.0/16 cannot find any an SLA member among its priority list and must fall through to members that do not normally carry Hub 2 traffic. At the BGP layer, the sessions from Spoke 1 to Hub 2 drop, and all prefixes learned from Hub 2, including the 10.200.0.0/16 prefix for Hub 2's data center, are withdrawn. BGP reruns best path. The same 10.200.0.0/16 prefix is still advertised by Hub 1, because Hub 1 learned it from Hub 2 via the hub-to-hub BGP session before the failure, and that prefix propagated to all spokes via route reflection. But here is the critical detail. When Hub 2 failed, the hub-to-hub BGP session also failed, and Hub 1 therefore withdrew the 10.200.0.0/16 prefix that it had originally learned from Hub 2. So Hub 1's BGP table no longer contains 10.200.0.0/16. For Spoke 1 to still reach 10.200.0.0/16, either Hub 2's upstream connectivity needs to recover, or there must be a static or alternative route configured on Hub 1 for the Hub 2 data center subnet. In well-designed deployments, Hub 1 and Hub 2 are not isolated data centers but have a direct data center interconnect, or both hubs have reachability to the same data center subnets through some other means. So the 10.200.0.0/16 prefix is redundantly available. In those designs, the Spoke's BGP table has the prefix through both hubs and simply withdraws the Hub 2 path while keeping the Hub 1 path. Traffic for 10.200.0.0/16 then flows from Spoke 1 through H1_MPLS to Hub 1, and from Hub 1 through the data center interconnect to the destination. When Hub 2 eventually recovers, BGP sessions re-establish, prefixes are re-advertised, local preference kicks back in, and traffic migrates back to the direct Hub 2 path. This is the multi-hub design working exactly as intended. Operational Best Practices Summary. Let me close Part 2 with a set of operational best practices distilled from running multi-hub SD-WAN in real production environments. First, always use a consistent naming convention for tunnels, zones, and route maps. We used names like H1_MPLS and overlay_MPLS throughout. Consistent naming makes configurations readable, scripts reusable, and operations at scale manageable. Avoid one-off names for specific sites because they do not scale. Second, tune your border gateway protocol timers. The default border gateway protocol hold time of 180 seconds is far too slow for SD-WAN. Set keep alive to 10 seconds and hold time to 30 seconds on the neighbor statements, giving you border gateway protocol failure detection within 30 seconds at worst, and much faster when combined with bidirectional forwarding detection. The SD-WAN layer detects failures faster than border gateway protocol, but border gateway protocol also needs to converge for long-term routing stability. Third, always double-tag BGP routes with communities indicating both the source hub and the source transport. The examples we showed used communities 6500:100 for Hub 1 and 6500:100 for MPLS. Tagging gives you fine-grained path preference capability and, equally importantly, gives you visibility into where routes came from when you run Diagnose IP Router BGP show on an operational box. Fourth, test your failure modes before production. Deliberately power down a hub in a maintenance window, pull the MPLS circuit on a test spoke, and observe how traffic shifts and how long convergence takes. If the measured convergence time is outside your SLA commitment to the business, tune timers and retest until you meet the target. Never assume the design works until you have measured it under failure. Fifth, monitor the fabric with proper observability. Export BGP metrics via SNMP or the FortiGate REST API. Track the per-member SLA metrics from Diagnose Sys SD-WAN Health Check, and alert on tunnel state changes. A fabric with hundreds of tunnels will have transient issues, and you need to distinguish noise from real problems. Good monitoring is the difference between a robust deployment and a fragile one. Sixth, document your design. A multi-hub SD-WAN is complex, and the engineer who built it will not always be the one troubleshooting it at 3 a.m. during an outage. Write down the hub assignments, transport mappings, community scheme, and failure scenarios. Keep the diagrams current. Anyone responding to an incident should be able to understand the design within minutes. In the next part of this series, we will move into advanced topics: multi-region designs with regional hubs, integration with public cloud transit gateways, SD-WAN over SASE for secure internet breakout, and centralized management via FortiManager for deployments with hundreds of spokes. Please subscribe to the channel so you do not miss Part 3. Multi-region SD-WAN architecture. Welcome back to part 3 of the FortiGate SD-WAN multi-hub series. In parts 1 and 2 we built a dual hub design with full BGP routing and failover behavior. Please subscribe to the channel if you are finding this series useful, and hit the bell icon for notifications on future videos. Part 3 takes us from dual hub single region to the real-world global enterprise case. Multi-region SD-WAN is what you build when your company has branches on multiple continents and you need to avoid forcing Singapore traffic through a US hub to reach a Tokyo application. The patterns differ from dual hub in meaningful ways, and getting them right requires careful planning. Let me walk you through this multi-region topology diagram. The diagram shows the global fabric spanning 3 regions: North America, Europe, and Asia Pacific. Each region has its own pair of hubs deployed for local redundancy, mirroring the dual hub pattern we built in Part 1. In North America we have NA Hub 1 and NA Hub 2, which might live in AWS US East 1 and US West 2, or in physical data centers in Virginia and Oregon. These hubs serve all spokes within North America as their local aggregation point. A Denver branch office will attach to NA Hub 1 and NA Hub 2 as its primary hub pair. Similarly, Europe has EU Hub 1 and EU Hub 2, perhaps in AWS EU West 1 and EU Central 1, or in Dublin and Frankfurt data centers. These serve all European branches. Asia Pacific has APAC Hub 1 and APAC Hub 2, covering Singapore and Tokyo for example. The critical design element is the backbone that connects the regions together. This backbone can be implemented several ways. You might use a dedicated MPLS backbone. You might use cloud provider backbone services like AWS Global Accelerator or Azure Virtual WAN. Or you might build a mesh of IPsec tunnels directly between the hubs of different regions. In the diagram we show the backbone as a cloud connecting all 6 hubs. A critical branch in Denver connects to both North America hubs using the same dual hub design from Part 1. When this branch needs to reach a software as a service application hosted in Europe, its traffic flows to one of the North America hubs, then crosses the backbone to an EU hub, and from there to the destination. The branch does not build tunnels to the EU hubs directly because that would not scale. With 3 regions and dual hubs, each spoke would need 6 tunnels per transport, and the IKE overhead alone becomes prohibitive. AWS Transit Gateway Integration. Let me walk you through this AWS Transit Gateway integration diagram. Enterprises running their workloads in AWS often deploy the FortiGate SD-WAN hub inside an AWS VPC so that branch traffic lands directly in the cloud. The transit gateway then provides scalable connectivity from the hub VPC to all other workload VPCs. At the network perimeter we have branch FortiGate spokes, which are FortiGate devices at branch offices running the same configuration we built in Part 1. These branches connect over MPLS or Internet underlays up to the cloud resident hub. The AWS Hub VPC is a dedicated VPC that exists solely to host the SD-WAN hub infrastructure. Inside the hub VPC runs the FortiGate hub instance, which is a FortiGate virtual machine, typically a FortiGate VM license deployed as an EC2 instance across 2 availability zones for redundancy. This is where all the Phase 1, Phase 2, SD-WAN, and BGP configuration from Parts 1 and 2 lives. The FortiGate hub instance attaches to the AWS Transit Gateway using one of 2 integration methods. The first method is Transit Gateway Connect, which uses GRE encapsulation plus BGP for dynamic routing. This is the preferred method for SD-WAN appliances because it supports high throughput and native BGP route exchange. The second method is a standard IPsec VPN attachment, which is simpler but capped around 1.25 gigabits per second per tunnel and requires AWS managed endpoints. The AWS Transit Gateway itself is a regional hub that aggregates connectivity from multiple VPCs. The Transit Gateway connects to Workload VPC-A, Workload VPC-B, and the Shared Services VPC. Workload VPCA might host production application servers. Workload VPCB might host a data warehouse. And the shared services VPC typically hosts centralized services like DNS, Active Directory, and monitoring tools. When a branch office needs to reach an application in Workload VPCA, traffic flows from the branch FortiGate over an overlay tunnel to the FortiGate hub instance. The hub instance decapsulates and performs a BGP route lookup, sees that the destination lives behind the transit gateway, and forwards through the connect attachment. The transit gateway then routes to Workload VPCA's attachment and delivers the packet to the target instance. BGP runs over the connect attachment between the FortiGate hub and the transit gateway, which means all VPC prefixes automatically propagate into the SD-WAN fabric without static routes. The FortiGate learns 10.1.0.0/16 for Workload VPCA, 10.2.0.0/16 for Workload VPCB, and so on, and it redistributes these into IBGP down to all spokes. Branch offices then see cloud prefixes as reachable, and SD-WAN service rules can steer traffic appropriately. Cloud on-ramp patterns. Let me walk you through this cloud on-ramp pattern diagram. Cloud on-ramp refers to how branch traffic enters the cloud, and it is one of the most important decisions in modern SD-WAN design. The wrong on-ramp pattern leads to traffic tromboning, poor performance, and high egress costs. The diagram shows three distinct on-ramp patterns for a branch office that needs to reach a software-as-a-service application such as Microsoft 365. Pattern 1 is backhaul to data center. The branch sends all internet-bound traffic through the SD-WAN overlay back to the corporate data center, where it exits through the central firewall to reach the software-as-a-service endpoint. This is the traditional hub and spoke model applied to software as a service. It is operationally simple because all security inspection happens in one place, but it is performance bad because every packet makes a long detour through the data center instead of taking the direct path to the SASE cloud. Pattern 2 is direct internet access from the branch. The branch FortiGate performs local breakout directly to the internet for approved applications, bypassing the SD-WAN overlay entirely. This gives the best performance because the traffic path is the shortest possible, but it shifts the security inspection burden to the branch FortiGate itself. Each branch firewall must have the full security stack, which increases hardware requirements and makes policy distribution more complex. Pattern 3 is cloud-hosted hub on-ramp. The branch sends software-as-a-service-bound traffic through the SD-WAN overlay to a FortiGate hub that lives inside a cloud provider, typically in a region close to the software-as-a-service application. From the cloud hub, traffic exits through a cloud resident firewall and reaches the software-as-a-service endpoint over the cloud provider's backbone, which is often paired directly with the software-as-a-service vendor. This pattern provides centralized security inspection while keeping the traffic path short because the hub sits near the software-as-a-service destination. The key decision is matching the pattern to the traffic type. Trusted corporate traffic like enterprise resource planning or sensitive databases should use the backhaul pattern because security matters more than latency. High-volume video traffic like YouTube or Zoom should use direct internet access because the overlay adds no value but adds latency. Software-as-a-service applications like Microsoft 365 or Salesforce should use cloud on-ramp because they live in the cloud and benefit from the cloud hub being close to them. SD-WAN service rules, which we covered in Part 1, are what implement these policies. A rule matching Microsoft Office 365 application signatures can steer traffic to the Cloud Hub member. A rule matching Zoom can steer to direct internet access. A rule matching internal application destinations steers to the traditional data center backhaul. This per-application intelligence is why SD-WAN is fundamentally better than legacy VPN for modern software-as-a-service heavy enterprises. FortiManager for centralized operations. Let me walk you through this FortiManager architecture diagram. Managing a handful of FortiGates through their individual command line interfaces is manageable, but once you have dozens or hundreds of devices, Centralized management becomes essential. FortiManager is Fortinet's centralized configuration, policy, and device management platform for FortiGate fleets. At the management tier sits the FortiManager appliance, which can be a hardware appliance, a virtual machine, or a cloud-hosted service. FortiManager holds the authoritative configuration for all managed FortiGates and pushes changes on demand or on a schedule. Inside FortiManager, configurations are organized by administrative domain, or a DOM. An ADOM is a logical boundary that separates device groups. You might have an ADOM per business unit, an ADOM per region, or a single global ADOM depending on your operating model. The diagram shows two ADOMs, labeled ADOM Americas and ADOM Europe, each containing its regional device set. Within an ADOM, the building blocks include device groups, which group devices logically, policy packages, which are reusable firewall policy bundles, provisioning templates, which configure features like SD-WAN and IPsec, and CLI templates, which hold raw CLI snippets for anything the GUI cannot fully express. The policy packages and provisioning templates reference template groups. A template group is a bundle of templates including SD-WAN template, IPsec template, BGP template, and routing template, all parameterized with variables. When you apply a template group to a device, FortiManager substitutes the variables based on the device's metadata and generates device-specific CLI. The managed FortiGates tier shows the actual branch and hub devices. Each managed FortiGate has a persistent connection back to FortiManager over a secure channel using the FortiGate FortiManager protocol, typically on TCP port 541. Through this channel, FortiManager pushes configuration, retrieves device state, collects logs, and distributes firmware. The workflow for adding a new branch office becomes dramatically simpler at scale. Instead of handwriting command line interface for every new device, you define variables like branch ID, BGPAS, local subnet, and target hubs for the new site. You apply the relevant template group to that device entry in FortiManager. FortiManager generates the full configuration including Phase 1, Phase 2, SD-WAN, BGP, and policies. You install the generated configuration to the device with a single action. For auditing and compliance, FortiManager keeps a full revision history of every configuration change. You can see who changed what and when, compare revisions side by side, and roll back to any previous version if a change causes problems. This revision control is essential in regulated industries and highly operational environments. Zero-touch provisioning workflow. Let me walk you through this zero-touch provisioning sequence diagram. Zero-touch provisioning, or ZTP, is how you deploy a new branch FortiGate without sending a network engineer to the site or pre-configuring the device in a staging facility. A non-technical person at the branch plugs the FortiGate into power and the internet, and the device configures itself. The sequence begins with the logistics team shipping a new FortiGate to the branch office. The FortiGate arrives in factory default state with no configuration beyond the ZTP bootstrap code baked in by Fortinet Manufacturing. A branch staff member at the site unboxes the FortiGate, plugs the WAN port into the internet circuit, and turns on power. The staff member does not need any networking knowledge beyond following a one-page instruction sheet. The FortiGate powers on and executes its default boot sequence. It performs a DHCP request on the WAN interface to obtain internet connectivity, receives an IP address, and establishes basic internet reachability. The FortiGate then initiates a connection to FortiCare, which is Fortinet's cloud registration service. The device presents its serial number, which was registered by the logistics team or by the purchase process when the device was ordered. FortiCare authenticates the device and replies with the address of the FortiManager or FortiCloud instance that is designated to manage this device. The FortiGate then connects to the designated FortiManager over TCP port 541, presenting its serial number for authentication. FortiManager recognizes the serial as a device that has been pre-registered by the engineering team with all necessary metadata variables such as branch ID, region, target hubs, local subnets, and policy assignments. FortiManager responds by pushing the full device configuration. This configuration was generated from the template groups we covered earlier, with all variables substituted to match this specific device's metadata. The push includes Phase 1 and Phase 2 for all overlay tunnels, SD-WAN zones and members, health checks and service rules, BGP neighbors and route maps, and firewall policies. The FortiGate applies the configuration and attempts to bring up its IPsec tunnels to the assigned hubs. The tunnels come up, BGP sessions establish, and within minutes the device is a fully functional SD-WAN spoke with complete routing visibility to the enterprise fabric. FortiManager then sends a notification to the engineering team indicating that the device has successfully provisioned. The engineering team verifies operational health in a dashboard, and the branch is ready for business use. Total human time at the branch is typically under 10 minutes, and total engineering time is whatever you spent defining the metadata variables, which might be 2 minutes for a well-templated deployment. This workflow is what enables SD-WAN at 500 or 5,000 branch offices with a small engineering team. Without ZTP, the deployment effort would be overwhelming. With ZTP and proper templating, the scale becomes a matter of logistics rather than engineering bandwidth. Part 3 Summary and Series Conclusion. Let me close Part 3 by summarizing the key takeaways across all 3 parts of this series. In Part 1, we established the foundational dual hub design. We built IPsec Phase 1 and Phase 2 tunnels with dynamic hub and static spoke configurations. We enabled a DVPN for spoke-to-spoke shortcut tunnels. We organized tunnels into SD-WAN zones by transport type. We configured performance SLA health checks and wrote service rules that steer traffic based on SLA compliance or explicit priority ordering. In Part 2, we layered dynamic routing on top of the underlay. We configured IBGP with a shared AS across hubs and spokes. We made the hubs route reflectors so routes could be redistributed among clients without a full mesh. We tagged routes with BGP communities by hub and transport source. We manipulated local preference based on community matches to steer traffic preferences. We walked through MPLS transport failure and full hub failure scenarios and saw how SD-WAN and BGP converge together to maintain connectivity. In Part 3, we scaled the design to real-world enterprise scope. We extended dual hub to multi-region with regional hub pairs connected by a global backbone. We integrated with public cloud transit services including AWS Transit Gateway and Azure Virtual WAN. We designed cloud on-ramp patterns for different traffic types including backhaul, direct internet access, Cloud Hub, and SASE. We added FortiManager as the control plane for configuration templates, variable substitution, and policy packages. Finally, we covered zero-touch provisioning for deploying new branches at scale without engineering site visits. The patterns we covered are not theoretical. They are the exact designs running in production at banks, retailers, manufacturers, and cloud-forward enterprises around the world. The FortiGate platform supports all of them, and the CLI configuration we showed is what actually gets pushed to devices when you deploy these architectures. A few principles apply across all 3 parts and deserve emphasis. Design for failure explicitly, because a multi-hub design that has never been tested under failure is not redundant, just apparently redundant. Tag your routes with meaningful metadata from day one, because BGP communities are the currency of traffic engineering and retrofitting them later is painful. Automate everything possible with FortiManager templates and variables, because manual command line interface does not scale past a few dozen devices. And finally, match your SD-WAN pattern to your application profile, not the other way around, because forcing cloud traffic through legacy hubs defeats the purpose of modernizing in the first place. Thank you for your attendance. Please consider subscribing to the channel and liking this video.